Hello, everybody. Just hope all is well. Hope everything's going good out there. I'm just taking a little side lecture here. This is going to be probably part one of a part 5 or 10 lecture series here. This is going to be based on Einstein's field equations, which is very interesting. So let me just say, so as you all are aware, I am definitely highly interested in the real life version of the TV series Stranger Things. I'm sure many of you guys are very, very big fans of the show. I'm definitely one of them. But it's definitely interesting because if you take a look at some of these, or some of the things that happen within this series, especially during season one, so definitely go back and check out season one. But this TV series is actually based upon two secret government projects. So, let me just say a little side note here. Change the Stranger Things logo into field equations. So this will be about Einstein's field equations, and how Einstein's field equations were actually one of the most important equations that were used in both of these two government projects. So the first project would be the Montauk project, or sorry, Montauk project. Sorry about that. I don't know why I said that. I was thinking, for some reason, I was thinking about Coriopolis for a moment there. So the Montauk project, and as well as the Philadelphia experiment. So if you would like to know more about these two projects, you just do a quick search to find out more information. Find some videos on YouTube as well. Some of these experiments that were done were pretty, extremely disturbing. So it's definitely going to be an interesting topic here, guys. So these two projects base their experiments off of many theoretical equations, the most important of which being Einstein's field equations. So this video is going to be about the derivation of such equations, and now that there will be some extremely complex mathematics involved within this video. Thus, if you're not interested, no worries at all. If you are interested, though, sit back, hit those lights, and enjoy, and remember, always be mindful of the world around you. So let's take a look at Einstein's field equations in all of their glory. So we have R of mu nu minus 1/2 of G mu nu times R plus G of mu nu times this interesting constant value. And that is equal to 8 pi G. It's actually supposed to be C plus, or C to the fourth, you could say, of T mu nu. So it's definitely an interesting equation. So let's think about this equation for a second. It actually took Einstein 10 years to develop these equations, and he had access to a plethora of mathematical geniuses of the world. And now I've made this video with the assumption that you understand advanced calculus and basic geometry, which I know may be a stretch. However, it is the only way to derive these equations. So let's discuss two key points that you must understand before we move on. Like I said before, advanced calculus and basic geometry, it's definitely a must for this lecture. If you don't understand those, no worries. It'll just be might be rather difficult for you to follow along, but it'll definitely be interesting nonetheless. So let's definitely get into that. Like I said, let's discuss two key points before we move on that you must understand. Let's talk about first. This one is known as the principle of equivalence. So this states that if you are confined in an enclosed box without the presence of windows, then you will not be able to tell whether or not you are in outer space accelerating with an acceleration of g, or being within the same enclosed box on the surface of the Earth, remaining stationary, but are being subjected to the gravitational force, which also carries an acceleration of g. So let me see if I can get this working again. I hope I can. Sometimes this is a little iffy. Let's see here. We're going to try to put this back in. See if I can get it in here. I want to be able to get the drawing aspect back on the screen again for you guys. That should be okay there. Yeah, so we'll be okay. Yeah, we'll be okay there. All right. So just to reiterate, so the principle of equivalence states that if you are in a confined enclosed box without the presence of windows, then you will not be able to tell whether or not you are in outer space accelerating with an acceleration of g, shown here on the right, or being within the same enclosed box on the surface of the Earth, remaining stationary, but are being subjected to the gravitational force, which also carries an acceleration of g. It's definitely interesting there. So at the present time, no experiment exists that you can perform that allows you to distinguish between the two aforementioned situations. This, in a manner of speaking, actually is not 100% true. So the difference between these two situations is, of course, if you were in outer space traveling with an acceleration g, then all portions of the enclosed box you are within, including yourself, will be accelerating at the acceleration rate of g. On the other hand, if you are located on the surface of the Earth enclosed within the same box, then because the value of g varies according to the height above the Earth, the value of g at the surface, right here, will be ever so slightly greater than the value of g at the top of the box that you are within. Thus, there will be a slight difference in the value of g in this situation that you're being, of you being within an enclosed box on the surface of the Earth. And if you can measure that slight difference, then you'll be able to tell whether or not you are in outer space or on the surface of the Earth enclosed within a box in the absence of windows to view the outside world. The difference in the value of g from the bottom of the box, or the surface of the Earth here, to the top of the box is known as the tidal force. So apart from that, Einstein stated that what I have just described to you is the principle of equivalence. You cannot tell the difference in whether you are accelerating at g or subjected to a gravitational force represented by the acceleration of g. So the second key point, which is definitely another interesting point here, is that light will bend when subjected to a gravitational field. Einstein's reasoning for this was if you take the person within the enclosed box that is accelerating through outer space with an acceleration of g. So here's the box here. You're accelerating. In this case, it's v here, but we'll say that v is g. So this time, we're going to shine a light from the left-hand side of the box to the right-hand side of the box. So from here to here. So we'll actually start from the center here, and then we'll work our way over. Of course, this will take a finite time, or in other words, an extremely small amount of time to occur since the speed of light is a massive number. If this box is accelerating with an acceleration of g, by the time the light reaches the midpoint of the box will have accelerated forward slightly. So take a look at this. So you can see the box moving up. So it's definitely a pretty interesting one. So the light will actually be located here, about 3/4 of the way within the box there. So this means that the light will have reached this position by the time the light reaches the right-hand side of the box. You can see over here. So this is when the light, the box is accelerating more forward. So obviously once it reaches this point, the box will accelerate slightly further. And now the light, which is of course propagating in a straight line, will reach this point. If you look at this light, it appears within the box that the light has gone from this point over here, which is near the center, and then this point, which the light would be a little slightly more downward towards the bottom of the box. And then when you reach this side, it has gone a little bit further down, almost down here towards the corner of the box. So in other words, the overall impression is that the light has gone from the center of the left-hand side, so here, to the lower right-hand side of the box, which is in the shape of a curve. So you can see the light started here, and as you accelerate, you generate this curve, which the light follows. Einstein stated that if this is indeed what happens when you are accelerating through outer space with an acceleration of g, since the principle of equivalence states that you cannot distinguish the difference between the aspect, or this aspect, and being stationary on the surface of the Earth subjected to a gravitational acceleration of g, then the same light should, or the same thing should happen in the Earth position scenario. Light will appear to bend under the influence of a gravitational field. Now, of course, Einstein could have been wrong about this, but in fact, this was shown to be true during a solar eclipse event. It's definitely very interesting. So let's take a look at that, guys. So what happens during a solar eclipse is that the moon essentially blocks the sun, so that from the Earth, the sun, as it were, is blocked out. And what was noted from the position on Earth was that they could observe a star just slightly off to the left of the sun. You can see here. However, astronomers knew that the star aforementioned was actually located behind the sun, and it should not have been possible to see this star since it was behind the sun. The explanation for this is that light from the star was being bent within the gravitational field of the sun, reaching us on Earth, giving the impression that the star was located to the left of the sun instead of it being located behind the sun to begin with. But the light was subjected to a bending influenced by the sun's gravitational field. So that's definitely a very interesting topic. So now here was the problem for Einstein at the time. Newton's law of gravitation, so we'll take a look at that. Everyone thought that this equation served us well for so long. It states that the gravitational force is equal to the gravitational constant times the mass of one body times the mass of another body, all divided by the square distance between the two bodies. This is fine, except that in the instance aforementioned, light is bending within a gravitational field. However, photons of light have zero mass. Thus, this form of Newton's law does not work if it is applied to light, since photons have zero mass. Einstein came up with a completely different approach to gravity. So we'll take a look at what Einstein came up with. So, instead of their existing gravity, actually what is happening is that all forms of motion are represented by movement within curved spacetime. So this can be illustrated with this graphic here. So, suppose we have a trampoline, or a surface of a trampoline here, this line at the top, which represents spacetime. Let's place a small marble on that same trampoline, so the next level down. This marble will virtually have no effect on the trampoline, maybe just an extremely small indentation of the surface of the trampoline. Now, third level down, let's suppose I get on the trampoline. If I get on the trampoline and exert my weight, the trampoline is going to bend quite substantially, and that is the equivalent of bent spacetime, or curved spacetime, if you will. So this aforementioned marble here will fall towards me. So this analogy is not exceptionally intelligent, but it will suffice for our purposes. So Newton stated that this movement of the marble towards me was caused by gravitational attraction. Einstein, on the other hand, stated, no, what is happening is that this marble is moving along the shortest path in curved spacetime, so that when the Earth goes around the Sun, Newton stated that there is a gravitational force between the Sun and the Earth, which provides the centripetal force that keeps the Earth in orbit. Einstein stated, no, that is not it at all. What happens is that the Sun, being a massive body, curves space-time, and the Earth is simply going around that curve in a straight line curved in space-time. So let's take a look at that. So basically, this is what Newton said. So there's a gravitational pull of the Sun on the planet, and this is the resultant path due to centripetal force. Einstein said, nope, that's not exactly what's happening. There's actually so the Sun, being a massive body here, curved space-time, and the Earth is simply going around that curve in a straight line within curved space-time. So it's definitely a pretty interesting topic there. So you might be wondering two things, as I did when I first heard this theory. Firstly, what is space-time? Secondly, why did Einstein think that space-time is curved? Well, space-time is just space and time, all thought of as one set of coordinates. So basically, we usually think of having 3 dimensions. So that's represented by the 3 orthogonal axes. So we have x, y, and z, and an origin point here. So basically, we have 3 dimensions in space. We have up and down, back and forth, and side to side. However, if you add a time dimension to that, you obtain 4-dimensional space-time. The problem with 4-dimensional space-time is that it is very difficult to draw because we can only conceive 3D. So let's just cheat a little bit. Let's try to cheat the 4th dimension here a little bit. So basically, let's just draw 1D of time and 1 dimension of space, which is the x-axis. So we have time plotted here on the left, x-axis plotted here. So you could, of course, draw another dimension this way, back this way, but let's just leave it as 1-dimensional of time and space at the moment. Now, if you draw a constant velocity in space-time, you get a straight line. So you get this line here. Sorry, it's kind of hard to draw, but there we go. So we get that line there. So it's a straight line because distance divided by time, or constant distance divided by a constant time, which equals constant velocity. Now, if you accelerate in space-time, you get a curve, which is very interesting here. So this bottom one here, this is the acceleration in space-time. The reason, of course, being that acceleration means that the longer the time, the further you travel. Thus, there is a curve in the acceleration, and because gravity causes acceleration, it causes a graph which is curved in the space-time coordinates. Einstein's view was that, therefore, in some way, space-time must be curved if it is creating an acceleration which has the effect of creating a curve in those space-time coordinates. So it's definitely an interesting topic, guys. So this is just the introduction of a probably, I'd say, 5 to 10 part lecture series. If you guys definitely enjoyed this, definitely like, subscribe to the channel, definitely share the video if you can, comment your thoughts down below, definitely appreciate that. The music in the beginning and the intro is by Guitars and Ghosts. Definitely check him out. I will definitely provide a link to his channel in the description. Also, the music that you're about to hear at the end of this presentation is by Guitars and Ghosts as well. So definitely, like I said, definitely go to his YouTube channel, which is linked down in the description. Definitely give him a subscription. Give him a ton of likes, guys. Definitely comment on his videos. He's definitely an amazing musician. And definitely appreciate him allowing us to use his music on our channel. It's definitely awesome. We definitely believe in promoting smaller channels, which is, #1 in my book. All right, guys, if you like this video, definitely check out our Facebook page at World Weather Authority. Also, if you have the means to donate, please do so at paypal.me/worldweatherauthority. Anything helps, even $1. But if not, just even subscribing to our YouTube channel, following our Facebook page, and liking our videos definitely helps. All right, guys. Thank you. Never stop chasing.